In this notebook, we will use cross-validation to compare the various models that we will build. In the previous lectures on cross-validation, we directly implemented cross-validation using the k-fold function from scikit-learn. However, in this lecture, we're actually going to just use the cross-validation score function that is built into scikit-learn to implement k-fold cross-validation for our RMSE, or root mean squared error, score function. So I want to walk through that process now, and then we'll use that to actually compare our basic set of models we just constructed in the previous video. So I'm going to import the cross-validation score function, or cross-val score function from scikit-learn. This function will implement a k-fold cross-validation and allows us to pass in any scoring function we like. However, that scoring function has to match a certain API. The API that the cross-validation score function requires is that our score function should take a model, the X matrix, as well as the Y vector that we're trying to predict, and it should return a scalar describing the score. The root mean squared error can be computed by taking the square root of the mean squared error, where the squared error is the difference between the Y value and what we predict passing in the X value. So we can then use the cross-val score, or the cross-val score function, to take our model, and in this case we'll take the very first model we trained, the model that just used the number of cylinders. We will pass it our training data. We'll pass the cross-validation function our training data, as well as the Y value that we'd like to predict, and we'll specify our score function is the RMSE score function. And finally, we'll set the number of cross-validation splits to be 5. So this would be a 5-fold cross-validation. When we run this function, it returns each of the validation errors for each of the 5 splits. So we want to take the average to get an estimate of the average cross-validation error. We simply take the average of the output of the cross-validation score function. So that's here. And so 4.8766 ... would be an estimate, or is an estimate, of our test error that was constructed using cross-validation, in this case, 5-fold cross-validation. So in this notebook, we will use this cross-validation score function to compare various models. In the previous lecture, we also defined a function to compare models. So let me once more walk through this function. What this function is going to do is it takes our dictionary of models. It then constructs the training RMSE, so it computes the root mean squared error on the training data set using our RMSE score function. It also constructs the validation RMSE using the cross-validation score function from scikit-learn. And finally, it computes a test RMSE by evaluating our model in the test data. I want to stress you should not be doing this in practice. I'm actually looking at the test data here because I want to show you how the test data would perform compared to cross-validation and training data. However, if you were actually building a model by looking at the test data in the process of making your model design decisions, you could bias yourself to perform better on the test data than you would do in practice. This is sort of like if you were to look at the exam while studying, you might actually study differently in a way that will give you a higher score on the exam, but actually then the exam would not be a good measure of what you really learned from the class, right? So we really want to hold the test data out from the model design and training process. But for the purposes of understanding what's going on between, or the relationship between the training, validation, and test scores, I want to visualize the test data here. Just to be extra clear, I made the test bar a little bit transparent, so it should be a little harder to see because we really should not be looking at the test RMSE in the process of model design. We can now compare the 5 models we've just constructed, and these are the models we've constructed. We notice that as we add more features to our model, the training error, the blue column, continues to go down. We also notice that the red validation error and the test error that you should not be looking at, these are also going down as we increase the number of columns. And so for this data, it does seem that adding these additional columns does ultimately produce a better model. We are not yet overfitting. I also want to note that the training error is typically less than the validation and test errors. That is because we optimize the model for to minimize the training error. And so it is an underestimate of the test and validation error. So we use the validation error, the red column, as a surrogate for the test error. In the previous lecture, we also alluded to using the origin of where the vehicle was manufactured as an additional categorical feature, but I didn't actually walk through the process of doing that. So I want to walk through that here as well. So the first thing we'll do is actually add the origin. So if we look at the training data and the origin column, each car has a region or country of origin. And so there are actually only 3 regions or countries of origin in this data set, so USA, Japan, and Europe. These are categorical features, so we would use a one-hot encoder to translate that into a numerical feature that we can use in our regression model. So we'll do that here. We use the scikit-learn preprocessing one-hot encoder class, and we can inject that into our pipeline. And we can do this by adding an additional transformation in our select column stage of the pipeline. Here, the origin encoder uses the one-hot encoder class applied to the origin column. All right, so this is our pipeline. So we'll again take this model, we will train it or fit it to our training data, give it a name that is the name of all the quantitative features plus the origin column, and we'll say that to our collection of columns. All right, so the remaining step will be to add the vehicle name. So we did this in the previous lecture, but I'll walk through it once more. We're going to use a count vectorizer, which is going to implement a bag of words encoding. We'll add an additional select column operation, here using the count vectorizer applied to the name column. So we can define this model and then fit it again to our training data, and we'll save it with the name containing all the quantitative features before, as well as the origin, as well as the name column. And we can now compare all the models we've constructed up to this point. When we compare these models, we actually see a pretty neat trend. As we increased the model complexity, as we added more columns, we saw the training error continue to go down until the very end, where it actually dropped quite a bit. So this is a large reduction in training error between adding the location of origin to adding the name column. So the introduction of the name features, and this is actually not one but many columns, due to the bag of words encoding. The introduction of these columns had a substantial reduction in the training error, but that actually resulted in an increase in the validation error. So this pattern of a big reduction in training error and an increase in validation error is indicative of overfitting. So at this point, we appear to have overfit. And in fact, if we look at the test error, and again, we shouldn't, but if we were to look at the test error, we also see the test error is starting to go up as well. So this is overfitting, and this is what we ultimately want to address with the introduction of regularization. What I didn't do in the previous notebook is actually examine the features. So I want to do that now. So I can go back to each of my models. So I'm going to get the names of each of the models, and I'm also going to get the final model, the linear model at the end of that pipeline. And I'm going to extract the coefficients for that model. So this is the number of parameters. And I'm going to take the length of that, and that's going to tell me how many features were in that final model. So if I plot this, and I'm plotting this on log scale, so the model which had just one feature, C, had one parameter. I'm ignoring the intercept term or the offset term, so it had one slope parameter. And then when we went all the way to including the country or region of origin for where the vehicle is manufactured, that added 3 additional columns on top of the 6 that we had before. So that was 9 features in that model. And then when we added the name of the vehicle, we went all the way to 270 features, which is a pretty large number of features given our training data set. Right, so that's a big jump in features, and that explains why we'd expect to see a fairly substantial overfitting. In the next video, we will apply regularization to this model here, the one that substantially overfit with a large number of features, so that we can bring the cross-validation error below the cross-validation error of these other models. So we'd like to be able to make the red bar here go below this red bar, and we'll show that using regularization and this model, we can actually get something that is better than any of the models we had seen before.